All right, let's jump right in. We're doing something a little different today. Instead of just explaining a topic, we're going to learn how to read about one. And we'll be using a real AI research paper to guide us through one of the biggest ideas in LLMs right now, the mixture of experts.
You know that feeling, right? You open up an academic paper and your eyes just glaze over. They can be so dense, just packed with jargon and equations and charts. But here's the thing. Some of the most mind-blowing ideas are locked away inside these documents.
So that's what this explainer is all about. We're going to give you the toolkit to crack these papers open. We're going to take this real-world survey on mixture of experts, or MO for short, and learn how to pull out the good stuff, the key ideas directly from the source.
And we're going to do it using a really simple 4-step process. Seriously, think of this as your new researcher's toolkit. First, we'll start with the abstract. Then, we'll dig into the core concepts. After that, we'll figure out how to interpret all the visuals. And finally, we'll zoom out and look at the big picture. Easy enough, right?
All right, step 1, the abstract. Honestly, this is probably the single most important paragraph in the entire paper. It's like the treasure map, right? It tells you what the authors did, why it's a big deal, and what they found. It's the whole story, just in a tiny nutshell.
So, what does this abstract tell us? Well, it lays it all out. It says MOE is a way to build these gigantic AI models, but without the insane computational cost that usually comes with them. The core idea? It's actually pretty elegant. Instead of one giant brain trying to do everything, you have a whole team of smaller, specialized experts. In this paper, it's a survey, which means it's a gold mine. It brings together all the crucial research on MOE into one place.
Okay, now we're ready for step 2, defining the core concepts. This is where things can get a little technical. But don't worry, the trick is to build up our intuition first. We'll get a gut feeling for it, and then we'll connect it to the formal stuff in the paper.
This really breaks it down perfectly. Think about it this way. On one side, you've got a normal, dense model. It's like having one genius, a generalist, who has to solve every single problem you throw at them. Super powerful, yeah? But also super expensive computationally. Now, the MOE model, that's totally different. It's more like a team of specialists. And there's a smart router, the paper calls this a gating network, that looks at a problem and sends it to only the most qualified experts. That idea, that you only compute what's necessary, it's called conditional computation, and it is the secret sauce behind MOE's efficiency.
And that brings us right to the formal definition. So, inside a typical transformer model, you've got these things called feed-forward networks, or FFNs. What an MOE layer does is it replaces that standard FFN, and this new layer has two main parts. First, a bunch of experts, which are really just smaller FFNs themselves. And second, that super important gating network we just talked about, the router that sends the data where it needs to go.
Okay, so this leads to a really important question. It's a classic design problem the researchers had to crack. What happens if that router isn't very smart, especially at the beginning? What if it just gets lazy and sends every single task to the same one or two popular experts? Well, then the other experts are just sitting around doing nothing. You get this massive load imbalance, and the whole point of having a team is totally defeated. So, how do you fix that? This is where it gets really clever. The paper explains that when they're training the model, they add a special kind of penalty. It's called an auxiliary load balancing loss. It's basically a mathematical trick. The model gets punished if it overloads any single expert. This forces it, or encourages it, to learn how to spread the work out nice and evenly.
So how does that math actually work? Well, that loss function is basically looking at two things for every single expert. On one side, you have d sub I. Think of that as the actual amount of work an expert gets, the fraction of data it processes. On the other side, you have p sub I, which is the important score the router thinks that expert should get. The whole goal of the loss function is to push those two numbers to be as close as possible, to balance them out across the entire team of experts.
So yeah, long story short, the whole point of this complicated-looking math is just to make sure every expert is doing its fair share. No lazy experts on this team. It's all about making sure the model actually learns to use all of the specialized brainpower it has available.
Okay, let's look at another really interesting design choice that the paper brings up. It turns out there are two different ways to think about this routing problem. The classic way is called token choice. That's where each little piece of data, Each token gets to pick which experts it wants to go to. But there's a newer idea called expert choice, which completely flips that script. Now each expert gets to look at all the incoming data and choose the tokens it wants to work on. This is cool because it guarantees a perfect workload balance. But the trade-off is that some data might get left behind.
All right, so we've got the core theory down. Now for step 3 of our toolkit, interpreting the visuals. This is huge. A really good paper tells its story with its charts and tables just as much as with its words. Seriously, learning to read these things is like gaining a superpower.
Just look at this timeline, which comes straight from Figure 1 in the paper. It tells an amazing story. You see the first big idea back in 2017, then a few key breakthroughs pop up. But then, look at what happens in late 2023 and into 2024. It's an absolute explosion. When open models like Mixtral 8x7b came out, it just kicked off this massive wave of new models and new ideas. It really shows you how unbelievably fast this field is moving.
And this table, this makes that idea of sparsity so clear. Just look at the difference between the activated parameters and the total parameters. For a model like Mixtral, only about a quarter of the model is active at any given time. And get this, for DeepSeek V2, it's less than 10%. That is the magic of Mo right there. You get the knowledge of a gigantic model, but with the compute cost of a much, much smaller one.
Okay, we're on to our final step, zooming out to see the big picture. Because a really great paper never just talks about an idea in a vacuum. It connects it to the real world, to the massive systems you need to actually run it, and to all the places where it can actually make a difference.
And the paper is very honest about the challenges. It points out 3 big system-level headaches for Mo. First, there's computation. Managing a workload that's constantly changing is way harder than one that's just static. Second, communication. Just shuffling all that data around between the router and the right experts on all the different GPUs, that is a massive bottleneck. And third, you've got storage. Yeah, the models are sparse when they run, but you still have to find a place to store all 236 billion parameters of a model like DeepSeek V2.
This chart does a great job of showing how everything we've talked about fits together. The paper basically maps out the whole research area into 3 main buckets. You've got algorithm design, that's all the stuff about gating and loss functions. Then you have system design. That's the hard engineering work of solving those communication and storage problems. And finally, you have applications, which is where all this theory gets put to the test in the real world, and things like NLP and computer vision.
So, as we wrap up this tour, what's the big idea here? I think it's this. The real magic isn't just knowing what a mixture of experts is. It's knowing how to figure that out for yourself. It's about having the skills to dive into the source.
And now, you've got the toolkit to do it.
It's that 4-step process.
Start with the abstract, define the core concepts, read the story and the visuals, and then connect it all to the big picture. This isn't just for this paper. You can use this method on any paper, on any topic you're curious about.
The world of AI is moving at lightning speed, and all the best, most exciting ideas are coming out in papers just like the one we looked at today. So now the only question is, what are you going to decode next?